Hi, today we're going to get more definitions and then some examples. We've talked about the hinge and we saw that the hinge gives, if the connected members are n, the hinge gives n minus 1 additional equations, which will help solve for the reactions in the structure. Okay, now we have the new definition, which is a link member. What is a link member? A link member is a member connected by two hinges, one at each end. It's a straight line, and there is no load between the hinges. There is no moment between the hinges. If these conditions are satisfied, that it is a straight line, it's start and finish of hinges, and there is no load on the link itself or on the member itself, then we define it as a link member. Okay, and then this link member has forces, only axial forces, forces along the longitudinal axis of the member. It doesn't have any forces perpendicular to it. So the forces in this member are only forces in one direction, either tension or compression, stretching the member or compressing the member. So we have a link. If we have one line that has two hinges, but it's a broken line, it's not a hinge. Or if we have one straight line that will have two hinges at the ends, but it has one load somewhere on the straight line or on the link, it's not a link either because it has loads between the hinges. Okay. If we have a link and then there is a one link connecting at midpoint of the link, then it's not a link either because this link perpendicular to it will exert forces on the vertical link. So this is not a link either. Or if we have concentrated moment, it's not a link. If we have the member like this diagram, a link, inclined link, and then one member at the top, one member at the bottom, and the forces are only applied on the top or the bottom of the hinges. It's a straight line between two hinges, so it is a link member. Okay, or maybe one inclined member that has hinge at the top and hinge support at the bottom. Again, this is a link member. So the link member has forces in only one direction, whether along compressing the hinge, the link, or stretching it. So it has only forces along the longitudinal axis of the link. So if AB, which is the inclined portion, has support at the bottom, hinge support at the bottom, and hinge at the top, this one is a link. So because the link conditions are applicable to it. Okay, and then we only have one member force, which is F, along the length of the member. This is a force in the link member. Okay, because this one is inclined, so F is resolved in F cosine x, F cosine alpha in the x direction, F cosine alpha in the y direction. And so it is F, it's only one force. Okay, and if we would like to know if the link is in tension or compression, if the force if the forces outside the link are working towards the inside the link, so it's a compression force. If the works are going outside the link, then it's a tension number. So if the forces are facing each other, going inwards, it's a compression force. If the forces are going outside, they are pushing out, then it's a tension number. How we solve for structural analysis, how we solve and get the forces in the links and in other members, we have to define the structure, know the length, know the dimension of the structure, know the loads, and we would like to get the reactions at the supports, get the reactions as forces and directions too, forces and directions. whether they are in positive x, negative x, or positive y, negative y. Okay, so we define the equations and then define the number of unknowns. The main equations are the equilibrium equations, and if the rod hinges, then we have additional equations which are the ones related to the hinges. Okay, and then try to find the easiest way to get the reactions. Okay, so we have the equations sigma x equals 0, sigma y equals 0, and sigma naught equals 0, and enter in addition to intermediate range equation. If we cannot find an equation that from which we get an unknown directly, then we get two equations, have two unknowns, and solve with two that equation. Solve that equations. We get the two unknowns. If it is difficult, then we break the structure into smaller structures. If there are like intermediate hinges, so as we said before, we break the structure at the hinges into connect, connected structures. After we're done the reactions, if they are positive, then our assumption was correct. If negative, they are negative, then we put the reactions in the opposite direction to our assumption. Okay, and then we finally, eventually, to make sure that we have to make sure that our solution is correct. We sum up the reaction and make sure that sigma x equals 0 and sigma y equals 0. Okay, here is one example: one beam, roller at one end, hinges supported at the other end. It's 9 meter long, divided into 3 points. At first point to the left, 3 meter from the left, is a vertical lift in ton. Another 3 meter from the left, or 6 meter from the left, or 3 meter from the right. There is a force 10 square root 2 ton, and it's implied at 45 degrees to the horizontal. We would like to get the reactions. Okay, so now we're going to assume the reactions as y1 at the left support, y2 at the left support, and the right support. If the right support is a hinge, then it has two unknowns, y2 and x2. So assume x2 is going left, y1 and y2 are going up. Then we resolve the forces 10 square root 2 into x component and y component. 10 square root 2 multiplied by 1 over square root 2 and the x on the y, so this will give you 10 horizontally and 10 vertically. And at the first point, we have 10 found. Okay, so this is a structure. This is structural system, the beam, the forces applied in it, and the location of the forces to connect with the beam, and then the reactions. Y1 at the roller and Y2 and X2 at the hinge. Okay, there are no intermediate hinges, so we only use the three equilibrium equations. Sigma x equals 0, sigma equals 0, and sigma moment about any point equals 0. Then we solve, we sum up the equations and the unknowns. In addition to intermediate hinges, if there are no intermediate hinges in this case, we have number of unknowns y1, y2, and x2, which are 3, number of equations, which are 3 equilibrium equations. So if we have 3 equations for 3 unknowns, then we're able to solve the structure. Okay. The easiest way to solve the structure is to find one equation from which we get one of the reactions directly. Okay. Now, if we use sigma y, then we'll see two equations, two unknowns, one y1 and y2. If we use the sigma m equals 0 at any support, there are two unknowns, except if we make sigma moment at point B at the hinge equals 0, then two unknowns will be 0, then we only have one unknown. And so we solve for this unknown. Okay? Sigma x equals 0, assume the positive to the positive direction to the right. So minus 10 plus minus 10 minus x2 equals 0, x2 equals minus 10. Then x2 is 10 ton, but in the opposite direction that it was initially assumed. So sigma m1 equals 0, mb equals 0. Now we have x2 equals minus 10 ton. Then in order to get y2, y1, assume the positive direction to be clockwise direction, then minus 10 multiplied by 3 plus 10 multiplied by 6 minus y2 multiplied by 9 equals 0, which will give us y2 equals 10 pounds. Okay, now we talk moment about A, not B. So we have to announce x2 and y2. Okay. Then y2 equals 10. Sigma y equals 0, then minus 10 plus minus 10 plus 10 plus y1 equals 0. Then y1 equals 10 times. Then eventually to check out the solution, we make a check. Sigma m2 equals 0, minus 10 multiplied by 3, minus 10 multiplied by 6, plus 10 multiplied by 9 equals 0, then the solution is good. In the other actions, y1 equals 10 times, y2 equals 10 times, and x2 equals minus 10, which is 10 but in the opposite direction. So where it was as 2, so it is going in the right direction, in the positive direction. Another example, we'll take a break before we go for this example. Thank you.